It turns out that string theory is not a theory of particles at all, but a theory of the entire universe. This is all down to a quantity called the string tension. This is a free parameter in string theory, and most string theorists have assumed that it must be close to the Planck energy in order that strings can model gravitons. The higher the tension, the smaller the strings. If we set this parameter to be equal to 1 divided by the age of the universe, in Planck units, then the natural size of strings will be in the size range of the entire observable universe. This massive shift in perspective is possibly the third revolution in string theory. It would explain, among other things, the smallness of the cosmological constant and the rotation curve of galaxies. That is not to say, such a shift does not bring up problems of its own. The question is, whether this solves more problems than it creates. Modern superstring theory is not just concerned with one-dimensional strings, but also includes other objects such as two-dimensional membranes and higher-dimensional surfaces. We can model the universe at some slice of time as a three-dimensional manifold embedded in a higher-dimensional space. The action is given simply by the total surface area of the manifold, which means the Lagrangian density is the square root of the determinant of the metric tensor. We can use coordinates in which the past horizon lies on the surface of a light cone. In order to get an empirical action in our local neighborhood, we make a shift in coordinates from the cosmic horizon to our current position. After a Taylor series expansion, we find that the cosmological constant is naturally produced along with curvature terms. Each curvature term contributing two derivatives of the metric tensor. This predicts that the cosmological constant is approximately 1 divided by the square of the age of the universe in Planck units, or 10 to the minus 122, which is what we observe. Notice that the series expansion is in terms of the reciprocal of the cosmological constant, which is extremely large. Such a series cannot be truncated after a small number of terms, or it will make no sense. So our next step is to think about functions that this series could formally converge to. These functions of curvature are where dark matter enters the picture. From Einstein, we know that curvature must be related to the mass density. We also know that the equations must approximate to Newton's equations in the appropriate limit. Einstein's field equations can be considered the simplest linear equations connecting curvature to mass density. But there is a family of nonlinear functions which also satisfy the conditions. An example is shown. The curvature squared term is a shorthand for a Gauss-Bonnet term, which is a specific contraction of two Riemann curvature tensors, which avoids second derivatives in the action, an important thing in the quantized theory. The common thing about these nonlinear equations is that they deviate from Einstein's predictions at a specific radius given by this formula, in Planck units, which we call the modified gravity radius or MOG radius for short. For galaxies, this radius coincides with the radius at which we observe the supposed dark matter effects. For our solar system, this radius is far beyond the distance to the Voyager probe beyond the orbit of Pluto, so we would not see the effects nearby. This tells us that using Einstein's equations to prove the existence of dark matter is not valid, since this is precisely the radius at which we expect Einstein's equations to break down. This doesn't necessarily mean there is no dark matter, but the evidence for it is vastly overstated. When we do the algebra, we find that the simplest model predicts that beyond the MOG radius, the gravitational force no longer matches Newton's 1 over r squared law, but approaches a 1 over r to the 2/3 power law. This predicts a flattening of the galaxy rotation curve which, although not perfect, is a much better fit than the simplest Einstein theory. We should point out that the so-called Mond theory, as well as several others, also predicts deviations from Einsteinian gravity at the same radius. Part 3. Particle masses. Next, we turn our attention to another mystery. Why are particle masses, such as the electron mass, so small compared with the Planck mass? We can explain the smallness by extending our gravitational power series to include a Higgs particle with U(3) family symmetry. The Higgs fields become 3 by 3 complex matrices. One each for the charged leptons, the neutrinos, the up quark family, and down quark family respectively. An example of a potential involving all four Higgs families is shown, which is a 12th degree polynomial in the Higgs field. The alphas are constants close to 1. There is enough freedom to account for all the variation in particle masses and mixing matrices. It is expected that the constants in the Higgs potential will one day be derived from symmetry principles. After symmetry breaking, this predicts a mass scale for the fundamental particles as the sixth root of the cosmological constant in Planck units. This value is in between the electron and proton masses. There is a proposed unification of the Higgs field with gravity if we consider the Higgs as a metric on 6 additional bulk dimensions in which the membrane lives. This would explain why the cosmological constant appears both in the gravitational and Higgs sectors. The masses of the fundamental particles arise as eigenvalues of the Higgs matrices, and the mixing matrices arise as the eigenvector matrices. The prediction is fairly good for the charged lepton mass scale. The quarks are within a few orders of magnitude above this. The neutrinos, several orders below. So there is still the mystery of why neutrinos are so much lighter than the others. Thus far we have only predicted the general mass scale, not the precise mass ratios. There are 3 fundamental radius measures for a massive object: the Schwarzschild radius, which is the smallest distance near a massive object that light can escape, the de Broglie radius, which is the wavelength associated with a particle, and our MOG radius, which gives the distance beyond which gravity deviates from Newton. It is interesting to note where these values converge. The Schwarzschild radius and the MOG radius are equal for the mass of the observable universe. The Schwarzschild radius and the de Broglie radius are equal for a Planck mass black hole. The de Broglie radius and the MOG radius are equal for the mass of a particle in between an electron and a proton. Hence these 3 quantities cover all the important scales in physics. The first to write about such large number coincidences was Paul Dirac. This was before the cosmological constant and the galaxy rotation curves were even discovered. But these clues have paved a way to explain these coincidences. Let us examine a few objections to this proposal. One objection would be that with a string tension so small, the small gap between string modes would mean there would be an almost continuum of masses of fundamental particles. This is indeed a valid objection if we were talking of one-dimensional strings, but it is far from clear if this objection holds for higher dimensional membranes. A second objection could be that perturbation theory of strings only works with a high string tension. This is another valid point, but we already know that the perturbation theory is only an approximation. Another objection may be that strings or membranes must be small to model small particles. This is simply a misunderstanding of quantum theory. It also overlooks that a large membrane may have a smaller intricate topological structure rather like a Swiss cheese. This proposal has concentrated on trying to give an explanation for large number coincidences in physics without resorting to such things as multiverse or anthropic principles. It reveals a likely connection between dark energy, the so-called dark matter effects, and a reason why particle masses are so small. What are your thoughts? Are you convinced by these arguments? Please leave your comments below. Thank you for listening.